Okay, everybody. So this is going to be lecture, let's see here, lecture 2, week 5. So what we're going to be going over today is basically just enough of what we see in the zyBooks on binary numbers to get us through the currently assigned homework. So basically that's it. So binary numbers, uh, current zyBooks. So the current zyBooks is, I believe, chapter 2, part 1. So that's what we're going to be looking at. So I'm on my iPad so I can write, and it was a real pain to get to work, but you guys don't care about that. And we'll head over here. So here's zyBooks. And if we go into chapter 2, there's lots of sections here. And specifically, 2.1 through 2.5 is what's assigned. Okay, so we've definitely gone over ASCII and Unicode, and we've gone over general number bases, and we've gone over binary and hex and octal. And we were looking at unsigned binary numbers, I think, and also signed binary numbers to two's complement. So those are the sections that we have to get through today. So that's what we're going to do today. So let's figure out where we were. Um, yeah, okay. Yeah, this is all right. I think I'm going to detach the keyboard from my iPad and hope that nothing breaks. Wish me luck. Are we still there? Yeah. All right, good. Um, so anyway, we have done this stuff already, and we've learned about binary numbers. And I think where we left off was we wanted to talk about adding binary numbers in a little bit more detail. So let's flip over to the note page here and let's look at it. So we know that if you look at a binary number, I'm going to write one I don't know about. Let's just write one that's like 8 bits or something. So this is just an example binary number to look at. So we're all working from the same place here. So let's just say like 0, 1, 1, 0, 1, 0, 1, 0. Okay, so here's just a random binary number. I mixed some ones and some zeros in there. And what we know from before is that in terms of places, that this first digit here is basically the ones place. The second digit is the twos place. The third digit is the fours place. Next digit is the eighth place. Then after that, we keep going up by powers of 2. So the next one is going to be 16, 32, 64, and 128. And so because of this, we've learned how to translate this into a decimal number based on what place we're looking at, right? So we know that the number that's listed here is basically a 0 times 128 because there's a 0 right here. Oops, that's not what I wanted. I really hate how um, all the buttons are in a different place than they used to be here. Um, where's the point daddy thing? We don't have one anymore. They just ruined this entire thing, in my opinion. Okay, well, forget it. Um, so 0 times 128. No, I got to figure this out. Hold on. So I apologize. This is going to take me a second to figure out what's going on. Nope. Oh yeah, they just got rid of all the controls that you actually need in order to use this thing. Fantastic. Love to see it. Man. All right. well, forget it. I can't just keep looking for it. Um, so anyway, up here, you can see the 128 there, and that we have a 0 under there that we're pointing to, right? So the 128 has a coefficient of 0, basically. So if we are writing our number here, dang it, we are writing our number here, then we would have 0 times 128, but there's a 1 in the 64 digit, right? Right here, there's a 1. So that would be 1 times 64, 1 times 32. There's no 16, right? Because there's a 0 there. So 0 times 16, 1 times 8, 0 times 4, 1 times 2, and 0 times 1. So we've done this many times. If you only pay attention to the ones that actually have ones on them, we've got a 64, because 1 times 64. We've got a 32, because 1 times 32. We've got an 8, because 1 times 8. And we've got a 2, because 1 times 2. And so that's it, pretty much, right? So if you add those all up, you get 64 plus 32, which is 96. 96 plus 8 is 104, plus 2 is 106. So the number that we came up with here is that this is 106. So, we're pretty familiar with that. Where we left off was basically trying to add these numbers to other numbers and trying to show things like carries. So that's what we want to look at now. So I want to talk about adding binary numbers. And so in order to add binary numbers, like by hand, you basically have to remember how you learned to add numbers in the first place using just like, I don't know what I would call it, like long addition, kind of like long division, right? So as an example of regular adding that's not binary, right? In um, decimal addition sometimes requires carrying. I'll just write carries. Sometimes requires carries. So what's a carry operation? Well, if I write a couple digit number here, like let's just say 748, and I wanted to add that, and I want to add that to, let's see, a 1, and then let's say a 9, and then let's say a 4. If we want to do this, what you would do is you would add the 8 and the 1, and you would get 9, and that's fine. And then the next thing to do, sorry, I'm getting frustrated here with what's on my screen. Okay. Um, so you did 8 plus 1, which is 9. And then in the next column here, right here, we have the 4 and the 9. So we need to add the 4 and the 9. So we add the 4 and the 9. 4 plus 9 is 13, but you only have one digit here. So you write the 3 and you have to carry the 1, right? So we have to carry the 1 there. And then in our last step here, we're going to add everything in this column. So we have 1 plus 8, sorry, 1 plus 7 is 8, 8 plus 4 is 12. So 8 plus 4 is 12. So you put the 2 here, and formally, like you can think of just like we added another carry digit up here, but then there's nothing in that column, so it ends up down here. So we end up with 1239 there, right? And basically, those carry operations you need to do when you're adding binary numbers. So when we add binary numbers, we also carry. Okay, and so basically, our only digits are 0 and 1, right? So we only have 0 and 1. So basically what's going to happen is when you add, obviously, like a 0 plus a 0, that's just going to be a 0. If you add a 0 plus a 1, that's going to be a 1. If you add a 1 plus a 0, that's going to be the same thing, right? 1 plus 0 is just going to be a 1. And none of those need any carries. So you don't need any carries here. So no carry. But if you add a 1 and a 1, you are going to need a carry. So if you add a 1 plus a 1, that's going to be 2. But the way that we write 2 in binary is 1, 0, right? So that would normally be 1, 0 like that. 1 plus 1 is 2, and you write 2 as 1, 0. But we don't really want to think of it as the way that I just drew it. What we want to think of it as, oops, not quite what I wanted. You put the 0 down here, and then you would carry the 1. So you bring the 1 up in the next column, and then that'll eventually end up down here. Okay? And that's how you would add a 1 and a 1. Now, something that's going to happen from time to time is that because of carry operations, you can actually add 3 digits at a time sometimes. So if you ever have a 1 and a 1 and a 1, and we need to add those, 1 plus 1 plus 1 is 3, which is written this way. So when you do 1 plus 1 plus 1, you're going to have 3, which is 1, 1. You'll put the first one here, and you'll put the second one up here. And then, of course, you can carry that through and end up with 1, 1. All right, so that's trying to show you a carry. Oh my God, I fixed it. I mean, I almost fixed it. I didn't actually fix it, but I know what's happening now. No, I don't. Anyway, there and there, those are your carries, right? And then we just brought them down. I have no idea what just happened. There. So those are your carry operations. I want to label them as carry operations. So we will. So these needed carries. Right? So that's basically 1 plus 1 needs a carry, and 1 plus 1 plus 1. Those are what needs carries. Okay, now looking at it when you're just looking at one digit, it doesn't make a lot of sense. You really need to see examples that have more digits than that. So I'll do an example, and then we'll look at the zyBooks for more examples. So let's add. Some numbers. So what numbers? I don't know. Um, let's say 1, 0, 1, 1, 0, and 0, 1, 1, 1, 0. Okay, so we want to add these, and we're going to have to remember how to carry. So to add these, of course, we're just going to write 1, 0, 1, 1, 0, whatever that is, and 0, 1, 1, 1, 0. And we want to add these. Okay, and so we go through and we add them using like normal rules for addition here. So you add here first. So we have 0 plus 0, which is going to be 0. No problem. Then you move over to the next column. So we're going to add these two, the 1 and the 1. So 1 plus 1 is 2, of course. But we are going to write that as 1 plus 1 is 2. We're going to put the 0 here, and we carry a 1. Okay, and so you have to remember basically what you saw right here. 1 plus 1 is 0 is 0 here, 1 here. So you put the 0 down first, and then you carry the 1. So 0 plus 0 is 0, and then 1 plus 1 is 2, which you write as 0, carry the 1. And now you're on, of course, this column, which has a 1, a 1, and a 1 in it, right? I mean, maybe I didn't write that in the best way, but we got a 1, a 1, and a 1 in this column. So 1 plus 1 plus 1 is 3, which, as we showed here, 1 plus 1 plus 1 is 3, which you write 1, 1. So 1 plus 1 plus 1 is 3, stop, which is a 1 here and a 1 here, right? Because you need to write 1, 1. Next column. So we're here. So now we are trying to add everything in this column, which is a 1, 0, 1. So 1 plus 0 plus 1 is 2, right? So even though we're adding three things, they're not 1, 1, 1 this time, they're 1, 0, 1. So 1 plus 0 plus 1 is 2. We know that to write 2, you write 1, 0. So you put the 0 here, and you carry the 1. Then we're on our last one here, 1 plus 1 plus 0. That is another 1 plus 1 plus 0 is 2. So you write it as 0. What happened? I don't know. You write it as 0, and you would carry the 1, but you don't need to carry a 1 really, because that's just going to end up right there. So most people would not even write that last bit there. I have to undo what I just did here. Okay. They've really messed up Notability since I've used it last. So anyway, the result there that we get is finally this answer right here, 1, 0, 0, 1, 0, 0. And that's how it goes. So we're going to look over in zyBooks and see if we can see where we would have to use this. So let's go here. We already did these, right? Like, what's the next higher digit than 0, 0, 0? Right? 1, obviously. What's higher than 0, 0, 1? It's 2, but you have to know how to write 2 as 1, 0, and so on. So they walk you through that. They talk you through counting. We did all these last time, I see. We did some of these. We did some conversions. We did some other conversions. We did how many bits does it take. We did adding a binary. Okay, so here we have to add. And so they're giving you, they're not making you write it yourself, right? They are showing you how to add numbers here. So when they say add 12 and 1, then what's happening is, I can't really, don't have a pointer that I can point to, but you see that the top row is just for the carry bits, right? So that top row is only for this stuff. Okay, so those are your carry bits. And then these two are, of course, the two numbers we're adding. And then finally, the last one is going to be your answer, right? So let's go back. So with that in mind, where it says 4-bit number, 4-bit number, the two gray rows, those are the 12, they said to add, where does it say it? Oh, it says add 12 and 1. I couldn't I couldn't see it. Uh, add 12 and 1. So the top gray number 1100 is 12, and the next one is 1. So all they expect you to do is to fill out the carry bits and the result. So if you look at the first kind of row here, where I'm tapping in, or the first column here where I'm toggling the things, those are the things you have to change. So just look at the gray numbers. We have a 0 and a 1 in the far right column right? The far right column, we have a 0 and a 1. So 0 plus 0 plus 1 is 1. So you change this to a 1, and then you move over to the second column. So that's this column. So in that column, we have the two gray numbers are what we're looking at. 0 plus 0 is 0. So that's all done. So we move over to the third column. That's this one. So in this column, we have blue, and the carry bit is 0, and then 1, and then 0 in the gray numbers, right? So 0 plus 1 plus 0. 0 plus 1 plus 0 is 1. So you put a 1 in there. There's nothing to carry. Move on to the last row. And so we're here now, and we just have 0 plus 1 plus 0 again. So this is what we get, 1, 1, 0, 1 for our result. So if we check this answer, it's correct. Now they are going to get like harder as we go because we're going to have to carry, but we'll see it when it happens. So same thing as last time. So first column, we got 0 plus 1 plus 0. 0 plus 1 plus 0 is 1. Now on the next column, we got 0 plus 0 plus 1 is 1. Third column, so we're here now. We have 0 plus 0 plus 1, which is 1. And then finally, the fourth column, here we got 0 plus 1 plus 0, which is 1. So the answer we get here is 1, 1, 1, 1, which is 15, which is what it should be. So that's all fine. So we check that. Oops. I'm sure we're going to get some carrying soon. In fact, right now. So now we have to add 5 and 9. So in this first column here, you now have 0 on top plus 1 plus 1, right? So we got, maybe I can do this. Yeah. So if we're trying to add these by hand, we've got, right now, we have 0, 1, 0, 1, and then we're adding it to 1, 0, 0, 1, right? So when we add these numbers together, we add our first column here, we've got 1 plus 1, and 1 plus 1 is going to be 2, but we put the 0 here, and we put the 1 up here, right? So over on the left, we have a 0 here, but this has to go to a 1. So this is the first time where we've had to add the carry bit ourselves. So we have to add these carry bits to the picture basically to get credit for it. So this is where we are. Now we're looking at this column. So this column we've got 1 plus 0 plus 0, which is just going to be 1, and there's no carry. So we come down here, and we're just going to put a 1 there. And then now we are on to the third column. Look here. So we've got 1 plus 0. 1 plus 0 is 1. And there's no carry, so we put a 1 here. And then finally, we're on the last column, which is also a 0 plus 1, which is just going to be a 1, and there's no carry, right? So the only carry bit that we had was this one, right? And so you only see one that we had to change in the top row there. Okay, and we got it. So we're on to the next one. So we got, I don't know, we have 0, 0, 1, 0, and we have 0, 1, 1, 0, and we're adding. So just like before, first row, or first column, I should say, 0 plus 0 is 0. Second column, 1 plus 1. 1 plus 1 is 2, but we write it 0, 1. Third column, we have 1 plus 1. 1 plus 1 is 2. So again, you put a 0 and carry the 1. And then finally, the last column, you have 1 plus 0 plus 0, which is 1, and you put a 1 there. So in order to translate this over to the zyBooks, you have to put 1s here and here. And then in the bottom row, we have 1, 0, 0, 0. So there you go. And that's correct, right? So one thing you'll notice here is where it says, like right here, it says ignore fifth carry bit. We probably will have to ignore the fifth carry bit if they're telling us that, and we'll see what that means. So our numbers that we're adding are 1, 1, 1, 1, and 0, 1, 1, 1. And so the issue here is that you can't add these numbers and have the result fit in 4 bits, because if you think about it, this is already the biggest 4-bit number you could have. It's 15, you can't have any bigger. So that's fine, but something is going to happen a bit weird. So our first column, we have 1 plus 1. 1 plus 1 is 0, 1, right? Well, 2, which we write as 0 on the bottom and 1 that we carry. Then our next column, we have 1 plus 1 plus 1. So 1 plus 1 plus 1 is 3, which is a 1 here and then a carry 1. And then we move over here, we have 1 plus 1 plus 1 again, which is a 1 and a carry 1. And then here we have 1 plus 1 plus 0, which is 2. So it would be a 0 and then we carry a 1. That's what we would have to do. Now, what they're telling us, though, is to ignore the fifth carry bit, because we never write it, but like there was a carry digit like here to start with, right? That we never used. So when we go to write our answer down, what we do is in our bottom row, we write the 0, 1, 1, 0, right? That we've got here, the 0, 1, 1, 0, like that. And then in our top row for the carry bit, starting at the right, we have 0, 1, 1, 1, and there should be one more 1, but there's not space for it. So this right here is the fifth carry bit, but they did not leave space for it in their little applet. So that's why we have to ignore it. If you were actually adding the numbers, right, you would just bring the 1 down and you would have 1, 0, 1, 1, 0, but that's 5 bits and we don't have space for 5 bits. So this is what we get. All right, 5 and 15, same deal. So we should be okay at this now. So we have 0, 1. So we have 0, 1, 0, 1, 1, 1, 1, 1. All right, so same thing as last time, basically. You can kind of think as there being like a 0 for that first carry bit. We add that first column. 1 plus 1 is 2, so 0 here. Sorry, I'm going to switch back to the color. 0 here, 1 here. And then second column, 1 plus 0. 1 plus 0 plus 1 is 2. So 0 here, 1 here. Now we have 1 plus 1 plus 1, which is 3. You write it as a 1 here and a 1 here. And then you have 1 plus 0 plus 1, which is 2. And you write it as 0, 1 like that, but we're carrying that 1, so we're going to write it up here. And so what you need to fill in are these 4 and these 4, just like the previous example. So we got 0, 1, 0, 0 on the bottom and 1, 1, 1, 0 on the top. Okay, so that's what's going on. For the rest of these, we're just adding lots of numbers for practice. We can do a couple. So like 0, 0, 1, 0, 0, 0, 1, 0, we're adding. So we just go 0 plus 0 is 0, 1 plus 1 is 2, but you write 0, 1. 1 plus 0 plus 0 is 1, 0 plus 0 is 0. So you got 0, 1, 0, 0, check it. And that's all that's going on here. So I'm going to skip down and I'll do number 3. So we have 0, 1, 0, 1, 0, 1, 1, 1. Add those together. And we got 1 plus 1 in the first column here is 2. So you go 0, 1. Then you have 1 plus 0 plus 1, which is 2. So 0, 1. Then you have 1 plus 1 plus 1, which is 3. You write it 1 here, 1 here. And then you have 1 plus 0 plus 0, which is 1. So we got 1, 1, 0, 0. All right. On the last one, if we do the last one just because that's the one that's going to overflow, as they say, if you add these up, then, all right, starting from the first column here, 1 plus 1 is 2, so 0, 1. 1 plus 1 is 2, so you put the 0 here, 1 here. 1 plus 1 is 2, so you put the 0 here, 1 here. 1 plus 1 is 2, so you put the 0 here, 1 here. But this time, we're not limited to their little applet, so you would bring this all the way down and write it this way. So this is how you would write, I guess, 16 in binary. And they said in the instructions, a carry bit may cause the result to have 5 bits. Okay, so we'll just write 5 bits, that's all. At least they didn't say not to. So this is what we got, and that is correct. Okay, so that's what's going on here. We can read a little bit here about overflow. And so basically, overflow, we can write it. Definition. Let's see. When you add two numbers, and you would have like basically that 5th carry bit. You add 2 numbers, and the result is too large. And what's too large? So when I say it's too large, it's going to mean that it requires more bits than you have. Requires an additional bit to properly store the number. Then we say there was an overflow. And so when there's an overflow, your answer is going to be wrong. Like, for example, if you were looking at this last number here that we added, right? So this was an overflow. The result requires 15, sorry, not 15, 5 bits to store. So the result needs 5 bits. And so if we only had 4, these are the 4 that you would get. So we added the number, this number, which is 15, and this number, which is 1. The result is just 16. But if you only had 4 bits, then the result would be what I put the box around, which is 0, 0, 0, 0, which is 0. And so that's obviously the wrong answer. And the way you could tell that the answer was going to be wrong was because there was a carry bit here. The 5th carry bit was 1. So that 5th carry bit can basically detect if there's going to be overflow. So basically, if you have, this is an example. Let's say uh, two 4-bit numbers, and the carry bit, the fifth carry bit, the last one, is 1, then there was overflow. Okay, and that's going to be true in general, right? Similarly, if you had like two 16-bit numbers with two 16-bit numbers, if the, let's say, 17th carry bit was non-zero, well, which means 1, right? So I'll just say 1. So if the 17th carry bit was 1, then there was overflow. And so what overflow means is that your answer, assuming you only have 16 bits, is going to be wrong because you need 17 bits. Okay. Also, you can tell ahead of time if there's going to be overflow based on the size of the numbers. For example, um, the largest 4-bit number is 1111, which is 15. So anytime you add numbers that are going to add up to more than 15, there will be overflow. So anytime you add numbers that will be over 15, there will be overflow. So you can just add these yourself, or you can use this kind of idea that we just talked about here. So this is 2.4.10 overflow. So you can just add them. So like on number 1, we go 0, 0, 0, 1, 0, 0, 1, 0. You can just add them and just go 1 plus 0 is 1, 0 plus 1 is 1, 0 plus 0 is 0, 0 plus 0 is 0, right? Like that. And then there's just no overflow. That was fine, right? Um, the ones at the bottom look like bigger numbers here. So like if you do number 5, 1, 1, 0, 0, which if you think of the places, this is an 8 and this is a 4, right? So this is actually the number 12 here. That's what we have. So this is 12. And then the other number is 0, 1, 1, 1, which is an 8, a 4, and a 1. So 8 and 4, sorry, a 4, a 2, and a 1. So 4 and 2 is 6, 6 and 1 is 7. So this is a 7. So that's 19, right? So there should be overflow because that's over 15. But if you go and you add it, then we'll just get what we get. 0 plus 1 is 1. 0 plus 1 is 1. 1 plus 1 is 2, so you go 0, 1. And then 1 plus 1 is 2, so you go 0, 1. And that one comes down, and you get a 1. So that's takes 5 digits, right? So it's supposed to fit in 4, but because of this extra carry bit, that's overflow. So you can't fit 19 inside of 4 bits. You need 5. So that is where we, that's number 5. So that was overflow. Also, like on number 6, that's obviously going to overflow. It's like 15 and 15. Obviously. They said obviously too. Okay. Um, for the last one, they're just talking base 10. So two digit numbers. If you add 50 and you add 70, that's 2 digits, right? But when you add them, it's going to be 3 digits because you're going to go 0 plus 0 is 0. 5 plus 7 is 12. But because of that extra carry bit, it's not a bit this time, but because of the extra carry, you get 120. And so it takes 3 digits, right? So they were talking about 2 digit numbers, but the result is 3 digits, and that's what overflow is. Okay. So hopefully that was useful. Um, if you did not understand this, maybe you understand it a little bit better, or at least how to type in your answers a little bit better. And then let's move on. So basically, what we want to do is we want to be able to handle negative numbers. Okay. And so we need a way to do it. So 2.5, 2's complement. Confusing people since 1967. Actually, I don't know when two's complement was invented, so I'm not going to claim a year. But um, basically, the problem is simple here. Um, we don't know how to do we don't know how to do negative numbers at this point, right? So that's what we are going to learn how to do. Um, how are we going to do or deal with negative numbers and subtraction? And I guess the answer to that is that we're going to solve subtraction by adding negative numbers, and then we have to worry about negative numbers. So what I can say about that is what I just said. So first thing is subtraction is easy. Haha. Right? Why is subtraction easy? Because subtraction is just adding a negative number. Right? So you know this from many math classes, right? Like if I say, what is 19 minus 7, right? Okay, what's 19 minus 7? Oh, I don't know how to subtract, right? If you forget to subtract, uh, it's the same thing as uh, 19 plus -7, right? I guess should have written it that way over here too, where I could write 19 minus 7 is the same thing as 19 plus -7. So we're not going to do anything special to learn about subtraction. Um, so subtraction doesn't need any new things. So we don't need any new theory. And on your CPU, when they're building the hardware for a CPU, they don't make a subtractor. They make an adder, and then they know how to write negative numbers. Okay, so that's it. Subtraction's easy. But that leaves you with the other problem, which is how do we deal with negatives? So how do we write? I can't believe I just wrote write that way. Brain not working. Today's a hard day. How do we write um, negative numbers? And the answer is two's complement is what we're going to do. All right. Now, let me kind of motivate this a little bit. So one easy thing we could do, so this is kind of, I mean, they go over it right there, so it's not really off topic, but so forget two's complement for the moment. We're not talking about two's complement right now, but one simple but not good enough, okay, method for writing a negative number. And so this is what you would come up with first, okay? So one simple, not good enough method for writing a negative number is just to add an extra bit. So we just add an extra bit whose job is just to keep track of whether or not the number is negative. So what would that look like? That would look like this. So just imagine like a number. So this is what that could look like. So if you needed the number, let's say 6, okay, in, I don't know why I wrote number equals 6. So as a 4-digit number, you would have a 0 in the ones place, a 1 in the twos place, and a 1 in the fours place. So this is the number 6. Okay. And then, so let's say we made this a 5-bit number. Okay. So this is going to be 5 bits. The bit on the left is 1 if a number is negative. Okay, that's the scheme. So if I wanted the number to be 6, I would write that as, I don't know what I just did. I mean, I do, I erased, but I wasn't trying to. 00110. That would be 6. Okay, and this bit right here, this is going to be the sign. So the sign is 0, and we said we're going to put a 1 if the number is negative. Okay, um, so if we wanted a number to be -6, all you would do is you would just say, okay, well, 011, that's 6. But then if we want it to be -6, you would just put a 1 here. Does that make sense? So this is one way to handle negative numbers, where basically this is 6, this is 6, and then you just have one bit at the front, and the bit just tells you if it's positive or negative. If it's 0, it's positive, and if it's 1, it's negative. Now the problem with this is that it doesn't make it easy to add these together. So the problem with this method is, how would we add um, plus and -6 and get 0, right? So the problem with this method um, is that um, you can't just add like normally. Now I'm going to make up an example to show this. Hopefully this actually does show this, because I'm just making up numbers off the top of my head. So like, for example, if we wanted to add the number 3 and we wanted to subtract 2, right? Then of course the number should be 1, right? Um, but if we try to do that with the scheme that we just came up with, the number 3 would be uh, 1, 1, right? That's 3. And if we need a bit to hold the sign, let's just say we're going, let's just say we do it this way. Dang it. I wish it wouldn't do that. Oh my God. Okay, so there's three, right? And then let's just say we add a fourth bit for the sign. So let's just say this is the sign bit, okay? So does that make sense? So we have a sign bit there. So that's three. And then let's say we wanted to add it to -2, right? So this is three, and now we want to put a -2. So -2 would be a one here and a zero, right? That'd be two. And then to make it negative, you would um, basically have to have a one there, right? That's how we said we were going to do negative numbers right now. Um, but then when we add these using the normal addition, we get 1 plus 0, right? We're starting on this side. Um, so we get 1 plus 0, which is 1. And then the next row or column, 1 plus 1 is 2. So you go 0, 1. And then you get 1 plus 0, which is 1. And then for the third, or for the sign column, you get 0 plus 1, which is 1. And so this is the result. And so the result is 1, 1, 0, 1. And of course, if you actually look at this first bit is the sign. And then the rest of it, 1, 0, 1 is a 1 in the ones place and the fours place. So this is 5. So the result that we got here was actually -5, right? So it didn't work, right? That's the point that I'm trying to make. So the point of this is that with the scheme that we came up with, you can't just add a negative number the same way you would a positive number. So with the simple scheme, you can't add negative numbers the same way that you would positive numbers. Okay, and that's a problem. We don't want that, because then if you were going to make computer hardware that worked with numbers this way, you would have to do something special to handle numbers that were um, to handle subtraction basically. So you'd have to do something fancy for subtraction. And nobody wants to do that, right? We would rather just be smarter at the beginning and not have to deal with it. And so that's why I said one simple but not good enough method is just to add that extra bit to the end, or to the front actually. Okay, so what's the right way to do it? The right way is choose complement, which is what we're going to do. So in practice, computers use 2's complement. Two, I'm going to say encode, but don't think of that way. So we use 2's complement to encode negative numbers. And the advantage to it is that we will just be able to add numbers. Okay. Um, an advantage is that we will just be able to add negative numbers and positive numbers and just get the right answer. Plus or minus numbers normally and get the correct answer. All right, so that is why we want 2's complement. Now, what is 2's complement? So let's go back. So, um, okay, All right, so read it right here. Here's the definition. The above is called two's complement representation. So what it says here is inverts every bit and adds one. That's how you do it. Okay. Um, so invert every bit, add one, and that's the two's complement version um, of the number. Okay. Oops, that's not what I want. Hold on a second. Okay. So here's how to do it. So to write the two's complement, basically encoding of a negative number. Let me go back here though. Okay. So to write the two's complement version of a negative number, step one is going to be invert every bit. Now, when we say invert, that means 0 turns into a 1 and a 1 turns into a 0. And then what you do is you add 1. Okay, so as an example, I'll show you an example first. So how do we write, let's see, a 4-bit, 4-bit, I'm going to say 5 bits, 5-bit. So one of the bits is signed, 1 bit. Actually, well, you know what? Forget it. I was going to say 1 bit is a signed bit, but we didn't talk about the signed bit yet. So we're just going to say, how do we write 5-bit um, number that's not correct? How do we write 5-bit number? What 5-bit number? Let's say 12 in 2's complement. Okay, so first, what would positive 12 be? Okay, so start with 12. Okay, now in a 5-bit number, right? 1, 2, 3, 4, 5. 5 bits, we know that, again, right, it should be easy. This is 1, 2, 4, 8, 16, right? 12 is just going to be 8 plus 4. So I can write this relatively easy without having to think too hard by just there, right? So that's going to be what 12 is, 8 plus 4. So you got to be able to do that first. So we got, here it is. So that's 12. Okay. And then the steps are going to be invert the bits. So we're just switching every single bit. So you go 1, 0, 0, 1, 1. Okay. So we inverted all the bits. So we're here now. And then your second step is going to be add 1. So you got to go 1, 0, 0, 1, 1, and then we have to add 1. And so this involves carrying and everything else like normal. So you got to know how to add. So starting over here, 1 plus 1 is 2. So you go 0, 1. And I guess I'll just put a bunch of zeros in here. So 1 plus 1 is 0, carry the 1. And then you have 1 plus 1 is 0, carry the 1. and then 1 plus 0 is 1, and then 0 plus 0 is 0, and then 1 plus 0 is 1. Okay? And so then that's it. So if we did this right, so if we made no mistakes, 12 in base 10 is what we said, which was 0, 1, 1, 0, 0, and negative 12 in base 10 so this is 2's complement, also 2's complement, is what we just got, which is 1, 0, 1, 0, 0. All right, and there's supposed to be a property that these numbers have. And so if I flip back over to the zyBooks, we could read about that property. And so the property is that when you add the numbers together, you are supposed to get, I can't, 1 and then a bunch of zeros. Okay, that's what's supposed to happen. And you're supposed to have n zeros. So if we were just adding these two 5-bit numbers, like we were dealing with 5 bits, then what we should get is 1 and then 5 zeros if we add those numbers together. So let's just verify that property. So note, if we add binary addition, um, these numbers, we're supposed to get 1 and then 1, 2, 3, 4, 5. Okay, that's just a property of 2's complement numbers, or a property of complements here. So that's a property that we should have. So let's just check it real quick. So if I go 0, 1, 1, 0, 0, and then 1, 0, 1, 0, 0, and we just add normal, regular binary addition here, then let's see what we get. So we have to start here. 0 plus 0 is 0. 0 plus 0 is 0. 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. 1 plus 1 is 0, 1. And then that comes down. So we got it, right? Exactly what I said was going to happen happens. So that's just a property of it. Okay. Now, so hopefully this process of conversion makes sense. You got to write the number as a positive number first. Then you invert the bits. Then you add 1. And then you've got the 2's complement version of that number. And so the 2's complement version will be the one that's negative, basically. So let's go back to zyBooks. Now, first of all, when they're talking about in base 10, what's the complement of 33? Well, if you think about it, what you're looking for there is the number that does this property, right? So if you're trying to figure out that example, if you had 33 plus what, those are question marks, what would give you 100, right? That'd be the equivalent to what we just did. And so the answer would be 77, right? That would give you 100. So these two are complements according to what they just said. At least hopefully that's what they want. Can I not add? Oh no, I can't. 67. 67. Okay. Try again. I want to fix that. Okay. Sorry. Addition is hard. Yeah. 67. Okay. All right. Now, the rest of these are going to just, I think, hopefully just make sense, like in terms of what we already talked about. So, like whatever one this is, 2.5.2, and then number 2. Um, if you have 0, 0, 1, 0, then what you do, you want the complement of it. So you flip all the bits, 1, 1, 0, 1, or so invert, and then we need to add 1. So I'll just go 0, 0, 0, 1, and we'll just add them and see what we get. So you're going to get 1 plus 1 is 0, 1. 1 plus 0 plus 0 is 1. And then 1 plus 0 is 1. And then 1 plus 0 is 1. So I get this for my answer. Okay, so we got it. So the next one, so number 3, what is negative 2 in 4-bit 2's complement representation? So we need to write negative 2. So we start with positive 2, which is going to be that. Hopefully we can get that far. So start with 2, invert the numbers, 1, 1, 0, 1, and then we need to add 1. So 1, 1, 0, 1 plus 1. 1 plus 1 is 0, carry the 1. 1 plus 0 is 1. And then we just bring those down. So we got 1, 1, 1, 0. Which I guess we technically knew because I said start with 2, but you know, that was 0, 0, 1, 0, which was actually the number in the previous problem as well. So of course it's the same answer. What? Oh, that was this one. Okay. We didn't do number 4 yet. Number 4, same deal. So this is negative 7. So we would start with positive 7. So positive 7 is a 4 and then a 2 and then a 1. So that should be positive 7. Then we invert 1, 0, 0, 0. And then we add 1. So we're going to go 1, 0, 0, 0 plus 0, 0, 0, 1. Sometimes I've been writing those zeros and sometimes I haven't. So we add 1 and we get 0 plus 1 is 1. And then 0, 0, 1. Ah, okay. Okay. Now, the thing about this is that the first bit will be 1 if you're looking at a negative number. So, note, first bit will be 1 if a 2's complement number is negative. All right. So here it says, assuming 4-bit 2's complement representation is 1, 0, 1, 1, positive or negative, the answer would be negative. And we know that just because it starts out with a 1, right? Left bit is 1, so negative. Okay. Assuming 2's complement representation, what base 10 number does 1 1 1 1 represent? Okay, so we didn't deal with this yet, but just to let's think about this. So let me look at the previous example. So the previous one that we did, um, notice we just did this one. 1001 is -7, right? That's from the previous problem, right? Start with 7, invert, add 1. Um, but what if you had to work backwards and wanted to know what 1001 is? So let's let's try to do this. So um, -7 is 1001. Okay, just saying start there. What if we do the same process again? What if I invert the bits 0 1 1 0? Okay, and then we add 1 again. So we have 0 1 1 0 plus 0 0 0 1, and we add these up and we get 0 plus 1 is 1, 1 plus 0 is 1, 1 plus 0 is 1, 0 plus 0 is 0. Then we get this number, and what number is that number? It's +7, right? It's actually what you started with um, up here. This is +7. Now, what does that tell us? What that tells us is, so no, um, if you apply, the process of coming up with a 2-bit number again. So if you apply the process, invert, add 1, um, you get back to the positive. Um, you get back to the positive number basically. And the reason that works that way is if you think about it, going back up, let's look at the one where we did decimal numbers, like right here. If you think about it, it's not just that you have the complement of 33 is 67. That would also mean that the complement of 67 is 33, right? Because when you look for the complement, you're looking for the number that you add and it gets you to a specific thing. So um, really, you have a number, and the two's complement version of that number are they're complements of each other, is how I should say it. So if you have a problem like number 6 here, so this is 2.5.2.6, and it says what base 10 number is 1111. And that's assuming 2's complement, right? Because if you were not dealing with 2's complement here, this number would be 15. But with 2's complement, it's not 15. So what you'd have to do is start with this number, which we don't know what it is, so I'm not going to say what it is, but you start with that number, 1111, invert the bits, so you get 0000, add 1. I'm not going to write it out because we're just going to add 1, so it's just going to be 0001. And that's 1, right? And that's 1. What does that mean? So the original must be -1. Okay? Because remember when we're dealing with these, right? Like the whole point of doing this is that like they wanted you to come up with -2 and you started with 2. So if we apply this process and we have a 1, then the original must be the -1, right? Because they're complements. So it's the negative of what we ever started, whatever we started with. So the answer is -1 there. Okay, and the same thing for number 7 here. So on number 7, we don't know what number 1001 is, but we know that it's negative, right? Because the left bit is a 1. So we do know it's a negative number, which means we have to convert it to know what it is. So what you would do is you would start with 1001, which we don't know what it is. We're going to invert the bits. 0110. We're going to add 1. Again, this is going to be easy, so just 0111 is what we'll get. So that we get this number. That number is 7. That's 7 in decimal. So the original 1001 must be -7. Okay, so that's the logic that we're applying here. So this must be -7. Okay. Now 8 is interesting because with 8, you have what is the complement of 0000? So we've got 0000, right? And if you apply the process, you would invert. So you get 1111, and then you have to add 1. So you go 1111 plus 0001. You add this all up. 1 plus 1 is 2, so 0, 1. 1 plus 1 is 2, so 0, 1. 1 plus 2, 1 plus 1 is 2, so 0, 1. 1 plus 1 is 2, so 0, 1. And you bring this down, and that actually takes 5 bits. But I guess they want, normally you would just take the rightmost bits there, so 0, 0, 0, 0. Or there's an error, depending, there's overflow, so there's an error. But if we're ignoring the overflow, then the answer would just be 0, 0, 0, 0. And so 0 is the complement of itself, basically. And that makes sense because the whole point is that you use 2's complement to figure out what the negative of a number is. But what's the negative of 0, right? The negative of 0 should be 0. So the complement of 0 is 0. So we started with 0 and we ended with 0. Okay. Number 9 here. I mean, there's nothing special here. It says, what is -3 in 8-bit 2's complement? So what you would do is you would start with 3, but we're in 8-bit. We're using 8 bits now. So we got 1, 2, 3, 4, 5, 6, 1, 1. Is that, did I get 8? Yeah. So so we get 0, 0, 0, 0, 0, like 3 and then 6 6 zeros. So we start with 3. What do you do after that? We invert all the bits. So 1, 2, 3, 4, 5, 6, 0, 0. And then we have to add 1, which you can do formally. And 0 plus 1 is 1. 0 plus 0 is 0. And I guess the rest are going to be 1. So 1, 1, 1, 1, 1, 1. So we got 6 ones. 1, 2, 3, 4, 5, 6. And then 0, 1. Okay. All right. So those are 2's complement numbers. I guess I can go for a few more minutes. And what they want you to do here is basically decimal complement. Um, all right, sorry, I was just reading. So let's get back here. So what we're talking about on these exercises, I want to get past them to get to the challenge exercises, but on 2.5.3, let's say point 1, first one, they say 6 plus 2 is um, 0, 1, 1, 0 plus, and so this is the 6, right? And um, they want you to say, well, you want to put the 2 there, right? So what's 2? 2 is 0, 0, 1, 0, right? That's the 2. And that's all you're doing there. Now, why is that all you're doing? Why is that all you're doing? Because we haven't looked at a negative number yet. So there's nothing to that one. Okay. So when you do the next one, 2.5.3.2, and they want 6 plus minus 2, right? How would you do that? Well, you have is the 6 is 0, 1, 1, 0. There's the 6 plus, and then how do you do minus 2, right? And so in order to get the minus 2, the number that goes here, what you have to do is the whole process of coming up with a 2's complement number. So start with positive 2, which is 0, 0, 1, 0, right? That's 2. Invert the bits. So 1, 1, 0, 1, and then add 1. So you got 1, 1, 0, 1 plus 0, 0, 0, 1. 1 plus 1 is 2, so 0, 1. 1 plus 0 plus 0 is 1, 1, 1. So you end up with 1, 1, 1, 0. So that'll be the minus 2. Okay, so that's all you're doing here. Like you can do all of the rest of them. So like if we jump to 5, I guess 2.5.3.5, right? They say negative 3 plus 2 is, and then what is it? Well, we need the negative 3 here and then plus the 2 here. And so they filled in the 2 just like before. We have to fill in the negative 3. So in order to fill in the negative 3, you have to start with start with 3, which is 0, 0, 1, 1. Invert the bits. So you get 1, 1, 0, 0. Add 1, which we do off the side. So we have, well, actually, we don't have to. 1, 1, 0, 1. There's no carrying or anything, so I'm just going to write it. And then there you go. So then that would be what minus 3 is. Okay, so yeah. Yeah, so basically, overflow, the way you can still have overflow if the numbers are too big. So with two's complement addition. And so the two cases where it's going to happen um, are going to be in this case. So basically, the way you can tell that it happened if the number's sign digit is wrong. So like, so we know if you add two positive numbers, right, the result should be positive, right? If you write that in terms of binary arithmetic, what that means is if you add two numbers with zero sign bit, the sign bit should still be zero. If it doesn't, then there was overflow. Okay, so as an example of that, right, we can come up with one. So like if I add these numbers, so like let's say I do 7 plus 7, not 7 plus 7. I want to make it a little bit different than that. So let's say I do 7 plus 5 in 4-bit, two's complement. Well, yeah, 7. So 4-bit, two's complement. So 7 would be 0, 1, 1, 1. Okay, that's 7. 5 would be a 4 plus a 1, so that'd be um, 0, 1, 0, 1. That would be 5, right? Now, when you try to add these, you go 0, 1, 1, 1, 0, 1, 0, 1. We add them, and we get 1 plus 1 is 2. 1 plus 1 is 2. 1 plus 1 is 3, so you go 1, carry the 1. And the fact that you just carried that 1 there is going to mean that 1 plus 0 is 1. So we get this number, 1, 1, 0, 0. And you can tell from the sign bit, we got a negative number. Because we know that that first bit is actually just kind of keeping track of the sign for us. And so the fact that that turned negative means that something bad happened, okay? Um, so we had overflow. So we didn't have enough bits to add 7 plus 5, is what it comes down to. Um, okay. Now, the same thing that we set up here, we also have the other way around. So like if I were to take this and bring it down here, we also know that if you add two negative numbers, the result should be negative, right? So, so if you add two negatives, the result is negative. So if you add two numbers with 1 for the sign bit, the sign bit should stay 1. And if it changes, then there was also overflow. So if you have two negative numbers that are too big or two positive numbers that are too big, then you can have overflow. You can't have overflow when you add a positive to a negative, though, because when you add like a positive to a negative, the magnitude gets smaller, right? Like 7 minus 5 would be 2, which is smaller than the other two numbers. So Um, when you subtract, when you have two opposite sign numbers, there's no issue. Okay. Um, if you add a positive to a negative, there should not be overflow. Because the result has to be smaller than the bigger of the two numbers that you wrote down. So with that said, they just want you to check if there's overflow here. So you just need to add them and see if the sign bit changes. So just looking here, on the first one, we would have to check because the sign bit is 0 in both cases, right? So we have to add them and make sure that it doesn't go up to change to a 1. On the second problem, we also have to add them to see if it's overflow. On the third one, we don't have to add them to see if there's overflow. Okay? Because the first one is a positive number and the second one is a negative number, and you can't get overflow in that case. So I know that that's going to be no overflow. The fourth one, where the sign bits are both 1, we would have to check that one. And then number 5 and 6 are seeing if we know what I just said. So problem 5 says number A's sign bit is 0. Number B's sign bit is 0. The sum sign bit is 1. Was there overflow? Yes, right? When the sign bit changes like that, it means there's overflow. Now it says number A's sign bit is 1. Number B's sign bit is 0. So they're opposite signs, right? One's positive and one's negative. If one's positive and one's negative, then like the last thing I said here, if you add a positive to a negative, there's not going to be overflow. Okay, so hopefully that made sense. Adding a negative and a positive cannot result in overflow. So the others you have to check. So you have to check them yourself. I'm not going to. I mean, it takes 2 tries, right? So it's an hour and 32. I'm going to do a couple of these and then we must be done. So answer with 1 digit. So what they're talking about here is complements again, like we did at the beginning. So we're dealing with 1 digit. So the complement would be what you add to get 10, right? So 3 plus 7 would give you 10. Binary complement. So they want it in binary, I think is what they want there. So this is 2.5.1 challenge. And we're doing number 2 right now. But yours is going to be different. So if you want the complement of 0, 1, 0, 0, we know what to do. You invert all the bits, 1, 0, 1, 1, and then you add 1, which you have to do by hand, 1, 0, 1, 1, plus 0, 0, 0, 1. 1 plus 1 is 2. 1 plus 1 is 2. 1 plus 0 is 1. 1 plus 0 is 1. So 1, 1, 0, 0. There are calculators for this, by the way, that we could be using. We just aren't. Binary complement. This one's being sneaky, right? 1100 is what we got for the answer for the previous one, right? Where we started with, where we started with this number. We started with 0, 1, 0, 0, and we ended with 1, 1, 0, 0. And now here it says binary complement of 1, 1, 0, 0. So I don't even have to do this one. If I do, I know it would get me back to where I started. Add. So this is just seeing if you can add. So add. Not a lot to it. So 0, 0, 1, 1, 1, 0, 1, 1. Add them. 1 plus 1 is 0, 1. 1 plus 1 plus 1 is 1, 1. 1 plus 0 is 1. 0 plus 1 is 1. 1, 1, 1, 0. And then it wrote them as decimal numbers. So in 2's complement, what it was doing there was 3 plus negative 5 is negative 2. Okay. Add them again. I mean, you can do that, right? Uh, 1, 0, 0, 1, 1, 1, 0. 0 plus 0 is 0. 0 plus 1 is 1. 1 plus 1 is 0, 1. 1 plus 1 plus 1 is going to be 1. And then there's overflow. So it would be 11010, but I don't know. They say answer with 4 bits. So just throw away that first one. So 1010. Yep, and there you go. And that was -4 plus -2, and the result is -6, which is correct. Okay. And you're going to have different ones, but 0, 1, 1, 1, 0, 1, 0, 1. Add them up. 1 plus 1 is 2, so 0, 1. 1 plus 1 is 2, so 0, 1. 1 plus 1 plus 1 is 3, so 1, 1. 1, 0, 0, 1. And so um, this one had overflow, right? Because notice that we had two positive numbers, right? You know that they're positive because their sign bit is 0. But if you look at the sign bit down at the bottom, we ended up with a negative number because the sign bit is 1. So we added them correctly, right? We did this correctly, but there was overflow, so the result is going to be incorrect. And so you can see what they got, 7 plus 5, and then the result that we got is -4 because of the overflow. So we made it through all of the exercises there. Took a long time, but we did it. So I think that's going to be it for today. So hopefully this is helpful. I know it was a slow start where I was being annoyed with notability. I really don't know what they did with the pointer, right? There's supposed to be a button I can press, not a button, but like a thing I can select to point at things that I'm writing instead of writing. But oh well. Um, that's going to be it for today. I'll talk to you guys later. And yeah, that's it. Later.